Okay, actually we can estimate the number of target count through the area. Okay, so we check the size of it, surface, we calculate the area. Okay, for example, if we think that maybe the size of the panel or block or the dissection would be good if it is roughly 1 meter width and the length, then we can use this number 70. So if it is 70 square meters, then probably we need 70 pieces. Okay, so we set it. Okay, then it'll be like this. And if we want to customize the edge so that all edges are equalized, then this dissection would be better if it is square, right? But anyway, I mean, it's really depending on the dimension of your original profile. I mean, it may not always be possible, but anyway, we think this quadri mesh will try to get the best we can have. Okay, so now we start with this. Let me save it. Okay, now we have to set constraints on the anchoring position. Okay, I would say let's simply get the corners. Okay, so curve, we find the discontinuity, which should be the corners. So the 4 corners. Okay, I think for Kangaroo simulation, very often the first thing I think about is where to anchor. So Kangaroo, anchor. Okay, the 4 corners. I mean, it really depending on how you are going to design your structure. And then we want to set constraints on the edge length. In the program, I use ghost line, so edge length. But let me see if I can use ghost mesh. Okay, no, it doesn't work. Because we want to control the size, okay? Ghost length. Because now here we can input the size of it. But before we input the size, I would like to derive the average size. Or maybe we can customize it. Okay, let's do classify, categorize them. So I check this edge size, mesh edges. E1 are the naked edge, E2 are the interior edges. So we have to join all of them. Okay. And I think this is trivial. I believe there are 2 different sizes, right? So let's try. Okay, see, I'm doing it differently, okay? Every time you have different design, you may think about different way of doing it. So it is not exactly the same way that I did on the previous program. So I would try to go to lunchbox, which is not this one. I need to go further. Lunchbox ML, machine learning. Okay, and k-means. And this time I would quite confident that we need 2 clusters, right? And all the input here is important. If you want to use k-means, you must know this. It doesn't like this input, right? And the reason is that you have to graph them. Why you have to graph them? Because right now we have only one value for each edge. Sometimes we want to classify them based on more than one attribute. For example, the length and perhaps also the thickness. Okay? Then for each element we want to classify, we need to specify more than one value. So in that case, if you put the entire set into one list, oh, sorry, I shouldn't do this. I should calculate the length first. But I think it can still do it. Okay, let me see. Yeah. Okay, let me try to make it more difficult. Well, it turned out this this quad remesh worked quite well. It always derives shape which is very much square. Okay, so now I think it works. With k-means, it also take lines. It will automatically calculate the length, but I think this is not. I think it is more safe doing this way. You calculate length and you classify on the length, okay, and the result comes very quickly. So actually, they are almost the same. So actually, we don't need to classify them at all because these two values are so close. And we can, sometimes we need to change the seed to check different way. I would say like make it 12. Okay, now it classify it in a different way, but still the two values are always very, very close. So I think in this case, I would simply ignore that. Say, okay? So if you classify them into one class, actually you don't need to do it. Sorry, so let me forget about it. I don't need them. Okay, but you still have to calculate the average of them, the average of all the lenses, and set it, oh sorry, here, and set the length as its constraint. Okay, and then now we want to simulate the anti-gravity, so we need to have a load which force all the vertices going upward. Kangaroo, goes point, load. Okay, by default, the force vector is a z vector going upward. So we need to find all the vertices. So to get all the vertices, we go to mesh, analysis, deconstruct mesh. Hey, if you can't follow me, get lost, you let me know. Okay? Otherwise, I just keep on going. Okay? V, by default, 1, I'm kind of worried because it is quite large. Let's start with maybe 0.1. Okay, let me use a slider, sorry. So that later we can adjust it. Okay, and then I will need a tree, data tree. I use ny so that I can maintain the branch structure. And I used to reserve the first one for the goals object which we need after the simulation process. Go to Kangaroo, which is you choose the geometry that you want to go through the process, which is the mesh. Okay, I think now we are ready. We are ready for the simulation. We get this simulation engine. We need a switch so that we can turn it off. We need a button to reset it. And then we connect the goals object. Okay, reset it, turn it on. Okay, now we derive the shape. Okay, and somehow if you have gravity, it is pushing inward. Okay, because yeah, but because we try to maintain the length of this edge, so it is not like minimal surface. Okay, let me show you one thing. If we try to minimize the length, if you say here 0, then the form that you derive will be similar to minimal surface. Okay? Okay, but here we don't use 0. Instead, we calculate the average length and then set to it. Then we derive this kind of shape, but still, I mean, it is kind of a structurally efficient because it derived the balance of all forces for this anti-gravity. Okay, so far so good, right? It's straightforward here. And now we have to go on to get the mesh. To get the mesh, before I used to use this tree explode, okay? But I think actually more, a better way, I have to say, a better way. It could take you more time, but it is a better way. We get the tree branch of it. And if we take a look at the output tree, okay, these are the indices of the branches. So we need to indicate these indices. But I think this case, we can simplify them. So you go here, click right mouse button, simplify. So now it is simpler. So to derive it, we need to specify the path. So one easy way, double quote, curly bracket, and then 0, and then curly bracket again. Then you get the mesh. Okay. Now we can start to check the mesh, to check the edge length. So go to mesh, mesh edges. We need to consider all edges, so we use the merge to put them together into one list. Okay, and we want to check this, the length, how much the length of this edge diverse, the diversity of the edge length. So we calculate the length of these edges. And then we find the average of them. Go to mathematics, average. And then how to assess the diversity. You have learned statistics, right? So what is standard deviation? Okay, this is one way to do that. But I think now we can use a simpler way, which is we calculate the differences between the length of every edge to the average. If you want to calculate standard deviation, then you need to subtract one from another, and then you square, right? You calculate the square of it, and then you sum up all the squares. Okay, but this time I think we simply get the absolute value, ABS. You know how to use this one? Okay, where to find all the functions that you use? Here. If you click, then you find a list. These are all the functions that you can use. And there's a short expression here. Okay? And or you simply use this toolbox here. Okay. So we calculate the absolute value of x minus y. And then we check the upper bound of it. So go to bound. And use the text panel to show it. Okay, so, well, it's too large. Okay? It's very diverse. So it's 22 centimeters. So we have to classify them, right? So maybe hopefully we can classify them into a few classes and then try to optimize the whole structure again so that to force each edge to be the same length of the average of the class which it belongs. Okay, so this is not acceptable. It is very large. Now we can bring our k-means, lunchbox. Oh, I have to get the lunchbox again. K-means clustering. Okay, or the lengths. Okay, remember we have to graph them, right? Input. And then how many clusters? We don't know. Let's assume 4 clusters. I also want to make seat. Okay, let me do one thing. I want the k-means to do the clustering more than once, every time using a different seed, so that I can compare which one get the best result. So we go to sequence, set sequence, and then maybe series. It create 10. Okay, let me, actually, I don't know if it is reasonable or not, but to me, I always like to use a large number. I mean, not to use a very small number for random seed. For example, I start with 25. And then each time I get 5. So it creates 5 numbers, 25, 26, 27, 28, 29. And I use them as seed. So what happened? Okay. So these are the average of each group it classifies. The first classification for the first group the first classification for the second group, the first classification for the third group, and the fourth group. Okay, and then we can check the average size of this. I would say if they are evenly separated, then that would be maybe it's a better classification. Okay, but this way it's difficult to compare. You understand this list? Get it? Okay? And I think it's better if we flip it. Flip it. Oh, sorry. Go to set. Flip the matrix. So it rearrange. So this is the first classification. And these are the groups. And maybe we go further. I want to sort them so that I can see more clearly how they classify them. So for the first classification, 1 meter 0.03, 1 meter 0.9, so there are 6 centimeters, and this one 8 centimeters and 13. Okay, which is okay. 5, 9, 13, 5, 9, 13. Okay. And you may also try different number of clustering. For example, if you want to try maybe not 2, maybe 3, then you get this 3. Okay. Okay, maybe let's try 3. And instead of making 5 clustering, we make only 1 cluster and then use it. Okay, 1 meter 0.3, 1 meter 14, 1 meter 30. Okay, we use these 3 clusters to constrain the length accordingly. So we have to use the Kangaroo ghost line. So now we have to tell every edge what is the optimized size of every edge. So for all the lines, the optimal size should be the average of the group, of the cluster. Okay, so where to get it? The result shows you the first edge goes to cluster number 1. The second edge goes to cluster number 1. And then the edge number 8 goes to cluster number 2. So we can use this number as the index to get the optimal size, which is supposed to be one of them, okay, using the index. So we go to set, okay, and we use this, use this result as the index to get the optimal size, okay. So now we get this list, and this list will indicate what is the optimal size of each edge. And then now we use this to constrain all the lengths. Okay? And then what we need to do, we need to try to maintain the shape, right, of the mesh, so that when it tries to adjust the length of these edges, the deformation is still under tolerable range. Okay, and how can we do it? We may want to let's go back. Go back to our first optimization. This is the direct result of the first form finding process, right? So this is supposed to be the optimal shape. So we get the mesh here, and we want to refine it. We want to refine because it is so coarse, right? And when the size of the edge are changing, the vertices will be moving. So we have to somehow make it smooth. How can we do that? Again, we go to mesh, and then quadri mesh. Okay, now we get a mesh which is refined. I mean, it matches this more coarse mesh, but somehow it tried to refine it. And if you are not satisfactory, then you can go on to increase the target count. But that will also make your computer more difficult to get the result. So we assume that this is okay. Then we go to Kangaroo 2. And this time, we want to constrain all the vertices to force them or try to make them fall on the mesh. This is the desirable shape. And we need to get the vertices of the mesh, so we go to deconstruct mesh. Where is the mesh? This is the mesh, right? Now make it more readable. Sometimes I do this extra work. So I bring this mesh and then link them so that I can bring it closer. It will take a little bit memory of your computer, but it makes you more easy to read your own program. So we need to, we need to deconstruct the mesh in order to derive all the vertices, so that we want to constrain these vertices so that they fall on this desirable shape. Okay, and we also need to anchor these four corners, right? So I assume that the four corners are not moved. So I can still use the original anchor position. But in some cases, if these points are moved, then you have to get it back, okay? But I think this time I assume that they are here. These are the anchor point. Kangaroo, anchor. I think that should be enough. We go to set and wine, put them together. I always reserve the first one so that we can show it. This light bulb, I want to show the mesh in the simulation. So this is, oh, sorry. Here is the mesh, right? Show it. Connect to this NY and kind of copy this. And then we use it again. It's too long.